Hi! Oh, Hi, ElectroBOOM, Mehdi here. Diodes. What are diodes? They are these brilliant components. And brilliant? Well, it's the sponsor of this video, where you can learn a ton of simple to complex math, science, and computing concepts with easy to understand interactive courses. Use my link. Diodes though, they were these massive breakthrough in electronics. You put 4 of them together and you get full bridge rectifier! Imagine for a long time we only lived with resistors, capacitors and inductors until we were tired of the linear behavior of impedances and decided to bend the curve. Diodes are these components that allow the current to flow one way and block it from coming back. Basically, they are the check valves of electric current. But how do they work? Well, we don't care at the moment. In olden times, they started making them out of vacuum tubes, which were pretty much replaced when semiconductors were created. I place a link at the corner to a video from Mr. Carlson's lab on vacuum tubes and Steve Mold's video on semiconductors if you want to learn deeper on how they work. Here, I just want to surf the surface and talk about what it does so we can design circuits with it. Silicon diodes are amazing though. You think they just rectify? Think again. There are millions of different types, maybe around 10, but they are all made based on the same concept. 2 different materials are fused to each other and the junction between them has magical properties. Fine, I go a bit deeper. Semiconductors are material typically made of silicon crystal that we dope them with small amounts of impurity. And depending on the type of impurity, we get positive or negative semiconductors. As their name suggests, they are conductive. They are electrically neutral, of course, but if we fuse the 2 types together, the p-type will happily pull electrons from the n-type, which is happy to give them, right at the junction. This creates a small region of charge imbalance called depletion region. So this means if we decide to put a positive voltage on the p side and suck electrons out, p gladly takes electrons from n and the negative terminal, and current flows with low effort. But if we flip the voltage across the p-n junction and try to force electrons into p, it won't want to pass electrons into n. That's not their deal. The p-n junction blocks the electric current. So we have a diode. Just try to remember the p and n behavior because it will later help you understand the behavior of all semiconductor components. P wants to suck electrons from N and N only. It doesn't want to suck electrons from the power supply. This is a marriage contract only P and N got into. Diode is generally shown with this symbol, like an arrow indicating the direction the current can flow, which is the reverse of flow of electrons, and how a reverse current will be blocked by this wall. This is also the symbol of a general purpose diode. You'll see that different type of diodes will have different symbols. Now let me show you the ideal behavior of a diode. X-axis is the voltage across the diode and Y is the current through it. If the voltage across it tries to get positive or the diode is forward biased, it turns on like a switch and lets through any amount of current like a short circuit. But if the voltage is negative or the diode is reversed biased, it blocks and there is zero current. Here's a typical through-hole diode. You see the gray line here indicates the direction of the diode. You see if I try to put the diode in reverse, the current reading is a bit off. It doesn't conduct and there is no extra current from the power supply. But if I flip the voltage, see, it is starting to conduct like a short circuit. Oh, it's burned. We must not exceed the power rating of the diode. So I'll place a 10K resistor series to it to limit the current. And now we can measure the voltage and current through the diode. For current, I'll just measure the voltage across the resistor. I don't know if you can see my resistor and diode in this mess of probes. And for my AC power supply, of course, I use the power lines. It's Fine. I put my scope in XY mode, X being the voltage across the diode and Y current through it. And it acts like a diode. For negative voltages, there is no current. And for positive voltages, it acts like a short circuit. There is current, but no voltage. Or is it? Let's zoom in on voltage. See? This is a real non-ideal diode. It takes a little bit of voltage before the diode starts conducting, which is different from diode to diode, and we can assume it to be around 0.6 volts for decent amount of current. But it's actually a little bit less for a smaller current and a little bit more for higher current. And after that initial voltage, the current ramps up. So we can approximate a diode's behavior like this. An ideal diode in series with a reverse 0.6 volt ideal battery we have to overcome, and a small series resistance. Or do like I do. When you use a diode, just understand that there is around 0.6 volts across it that can rise slightly when the current rises. We typically ignore this resistance for most applications because it's small. And we can also ignore this voltage if it is too small compared to the voltages in our application. Like if they give you this circuit and ask you to calculate the current, you can just assume the diode voltage is 0.6 volts, write a KVL as VBAT equals resistor voltage plus the diode voltage, or 2 volts is equal VR plus 0.6, and VR is equal RI, or equal to 1K times I, so I is equal to minus 0.6 divided by 1000, or almost 1.4 milliamps. And if they want it any more accurate, tell them to pull the soldering iron out of their butt, because nobody writes diode and accuracy in one sentence. Now I changed the series resistance to 100K for more precision, and let's zoom in on the current. Look at that, the current is not zero in reverse voltage. There is a very small leakage current in reverse. So we can add a very large resistor across the diode to model it. Although the leakage current is typically so small, we can ignore it. This time, let's zoom out on the voltage. Look at that. The diode that's supposed to block current in reverse voltage is conducting large amounts of current when the voltage passes above some threshold, around 100 volt in this case. The voltage where current starts flowing is called the breakdown voltage, and the region behind it is the breakdown or avalanche region. If you push the diode too hard in reverse, it starts conducting. That could be destructive to the diode. The reason diode dies here is because you would have very large reverse voltage and current through it, which results in very large power drop. It heats up quickly and blows up, unless you get out of that region very quickly. That can be modeled with a reverse ideal diode and a battery with breakdown voltage value. You have to be larger in reverse than this voltage for the diode to conduct backwards. We typically ignore this because we keep below that voltage level, because that's not a desirable effect. Until it is. We can make use of breakdown voltage. If it is a reliable known voltage, we can use limited current through it and create an almost fixed voltage, typically used as a reference voltage. And so we make something called a Zener diode. Zener diodes are designed to have specific breakdown or Zener voltages, like 1 volt, 5 volt, 10 volt, or whatever. In a circuit like this, a Zener diode will clamp the voltage close to its breakdown voltage, regardless of the input voltage. Well, as long as the input is higher than the Zener voltage. Here I have a 5 volt Zener diode series with some resistance, and if I raise the supply voltage, you see the Zener and supply rise together until around 5 volts. Zener starts conducting, the supply rises, but the Zener voltage is clamped around 5 volts. Zeners can be used to generate fixed voltages as references, or they can be used to protect the circuit against high voltages by clipping the large voltages like this. In case of protection, they typically call such diode TVS or transient voltage suppressors, which are much faster to react to transients and are more powerful. A single one called a unidirectional TVS like this is placed in reverse on signal lines to clamp over voltage like this. Two TVS diodes can be combined like this as one component called bidirectional TVS that can block the transient high voltage between a positive and negative breakdown voltage. But for regular diodes, we typically ignore all these and usually keep it at this level. Except, well, there is more. The thing is, if you shine a light on the PN junction, particles wiggle harder, sending more electrons from N to P, raising the voltage and affecting the diode's behavior. Like this diode's body is glass and the voltage across it rises when I shine a light on it. But we made use of that too, so diodes can be light sensors, or as we call them, photosensors. Did I mention they make voltage when we shine light on them? If we play with the chemistry and make them more efficient, we can draw energy from them, and we have solar panels. Renewable energy, here we come! But like Steve Mould mentioned in his video, if instead of pulling energy from them, we apply a voltage across them, they create light in infrared. Now we mess with the chemistry again and make them produce visible light. And we have LEDs! Efficient lighting, here we come! The only difference between LEDs and regular diodes is, well, beside the fact that they generate visible light, that their forward voltage drop is larger depending on their color. Otherwise, they could also be used as a poor man's regular diode. Oh, and remember when I said a diode blocks reverse current? If you look at the PN junction, there the depletion layer acts like a thin layer of insulation. So the diode acts like a capacitor holding charge. The width of depletion layer depends on the reverse voltage, which means adjusting the reverse voltage, you can change the capacitance. A variable capacitance based on the voltage across it. You design it better for this purpose and you get a varicap or varactor. Tuning the capacitance with voltage, you can create, for example, an adjustable frequency generator, maybe to make an FM transmitter. Semiconductor diodes, man, they change the world. But mostly when we say diode, we are referring to the regular current rectifying diode, or its cousin, Schottky diode, which has a much faster response time and lower forward voltage, so less power loss, but has a larger reverse leakage current, mostly used in switching power applications. There are other type of diodes I care less about. What I care more about though is Brilliant, the sponsor of this video. Brilliant, man, just brilliant. It's an awesome tool for learning simple to complex STEM concepts of math, science and computing easily. That's where I would go to remember all those things that vaporized from my brain, or to learn new stuff. Why? Because they made courses like games and puzzles and fun. A ton of interactive courses and quizzes to teach you what you would need for your school, job or interview. Like their brand new everyday math course, where they break down foundational math you would need for everyday life, to more advanced courses like neural networks, special relativity and such. So all ages and levels can learn well with all those interactivity. Psst. Give yourself and your family this gift from me. Use my link brilliant.org/electroboom to sign up and start trying Brilliant for free. And then get 20% off the annual subscription for full access. And start learning like you have never started learning before. And thank you for watching.